So NMR spectroscopy requires a strong magnetic field and radio wave energy. But what's interesting is that the strength of the magnetic field is going to affect the energy gap between the alpha and the beta spin states. So if I use a 1.41 Tesla magnet, the difference in energy between the alpha and the beta spin states is going to be less than if I use a 7.04 Tesla magnet. You might remember from general chemistry that energy is equal to Planck's constant times frequency. So we can see that energy is directly proportional to frequency. Also, we can prove that energy is proportional to the magnetic field. With a magnetic field strength of 1.4 Tesla, all of the protons in organic compounds will resonate over a narrow range of frequencies near 60 megahertz. If, however, a magnetic field strength of 7.04 Tesla is used, all of the protons in organic compounds are going to resonate over a range of frequencies near 300 megahertz. In other words, the strength of the magnetic field determines the range of frequencies that must be used. An NMR spectrometer that utilizes a magnetic field strength of 7.04 Tesla is said to have an operating frequency of 300 megahertz. Later on, we're going to see the advantage of using a spectrometer with a higher operating frequency. So we can see that since energy is proportional to both frequency and magnetic field strength, that as we use a stronger magnet, we get a greater difference in energy between the alpha and beta spin states, and our spectrometer will be said to be operating at a higher frequency. The strong magnetic fields that are used in NMR spectroscopy are created when a high current is passed through a superconducting material at a very low temperature. So you can think about the strong magnets used in NMR spectroscopy as just being very cold electromagnets. And you might remember from physics class that the greater the current, the greater the magnetic field with an electromagnet. The type of spectrometers that we use today are called pulsed Fourier transform spectrometers. And what they do is provide a brief pulse of radio energy of all the relevant wavelengths that can be used to excite the sample. And what it means by excite the sample is convert all those nuclei that are in alpha spin state to a beta spin state. But then what happens is that each of the atoms is excited and then it relaxes, emitting energy. So when it goes from the beta to the alpha spin state, we say that it relaxes and it's emitting energy. So it emits energy. And then that emitted energy is recorded as what we call a free induction decay, or an FID. The free induction decay, or FID, contains all of the information for each atom. And then what we do is a complex mathematical treatment to that FID, which we call the Fourier transform. And the Fourier transform separates the signals so that an individual signal can be observed for each atom that was excited. Normally, we pulse the sample many times with electromagnetic radiation and take multiple FIDs and then average them together. In order to run an NMR on an organic compound, first the sample has to be prepared neat or in a liquid solution using a deuterated solvent and then placed in a small NMR tube. What neat means is a liquid sample that doesn't have any solvent, so it would be a pure liquid. Then the sample is placed into the magnetic field and the tube is spun at a high rate to average out magnetic field variations or any imperfections in the NMR tube. There's a good reason why we use deuterated solvents in NMR spectroscopy. Although the nuclei of deuterium do exhibit nuclear spin and do resonate, they absorb radio frequency radiation over a very different range of frequencies than protons do. This down here is a picture of what an NMR spectrometer looks like, and it says here that you have the superconducting magnet cooled by a liquid helium. Well, there's actually 3 chambers inside the NMR spectrometer. So the first one, or the innermost chamber, has liquid helium in it. Then you have a chamber outside of that which has liquid nitrogen in it. And then outside of that you have one that's basically a vacuum. And that allows us to keep the magnet at a very cold temperature. Then we have a radio frequency generator. And then a computer processes the FIDs via the Fourier transform.